Okay, so welcome. You've heard my voice in a lecture. You have yet to see my face in a lecture. So I am Jeremy. I am the instructor for this course. As I have said on the, I don't know why I'm pointing to my computer as you can't even see it. As I have said on the PowerPoint lecture, my name is Jeremy. I know I'm technically Dr. Secant. You do not have to call me Dr. Secant. In fact, I kind of prefer if you didn't call me Dr. Secant. Jeremy is just fine. I'm perfectly content with Jeremy. There's no need for Dr. Secant. We're all adults, and we can maintain that level of respect without you having to refer to me as Doctor or Mr. or anything like that. So, without further ado, let's go ahead and get started. This is Chapter 2, Tools in Economics. Section 2.1 Introduction. We're going to cover a few definitions here. The first one is a set. A set is a collection of objects. It's typically denoted with a capital letter. And if we are going to explicitly define the set by showing all the elements within the set, we will be using curly brackets. Sets can be finite, they can be infinite. They can be countable, like the integers or the counting numbers. They can be uncountable, like the real numbers, right? If something is uncountable, there's no next element. If something is countable, well, there is, in fact, a next element. Another definition. Cardinality of a set refers to the number of elements in the set. For example, I wanted the cardinality of x, which I will use the letter, or the name of the set, in this case it's a capital X. I'll put two vertical bars around it to denote the cardinality. The cardinality of the set X is 4 because I got 1, 2, 3, 4 elements. This symbol here, this little epsilon, means is an element of or is contained in. For example, you can say A is contained in the set X. Because if I look at the set X here, you can see A is right here. I can do the same thing for B. B would be contained in X. If I want to say B is an element of, or B is contained in X, I would write that. So I've got A, B, C, and D inside this set X. Well, E is not an element of X. So I would use this epsilon with a slash through it to indicate this is not an element of X. This is not contained within the set of X. Now, as I go through some of the definitions at the beginning of this chapter, you will see that I skip by a couple of them. If you look at this lecture and then compare the lecture to the book, you will see there are a few things that aren't going to be mentioned in this lecture. That's because this book is still, in fact, a work in progress. And I have that stuff in there as of right now, but I'm not entirely convinced it will be needed, and I'm fairly certain it will not be needed for this course in particular. So don't worry about that stuff. Okay, let's talk about open interval. Now this may be new for some of you, this may not be new for some of you. For those of you that it is not new for, enjoy what you're seeing. For those of you that, did I say it's not new for, or is new? If it's new for you, it's interesting, important stuff. If it's not new for you, well, it's still interesting and important stuff. And if you think you don't need this, you can go ahead and skip past some of this stuff. I will leave a little marker in the YouTube video explaining when some of these definitions will end and when you can skip to the next section. Now, if I have this open interval from 0 to 1, this contains every real number between 0 and 1, but it does not contain 0 or 1. A closed interval, on the other hand, call it 0, 1, contains every real number between 0 and 1, and including 0 and 1. So this interval does not actually contain 0 or 1, it's everything in between. This interval does in fact contain everything between 0 and 1, including 0 and 1. And here comes the important part. Calculus. Trying to make these all uppercase. Derivatives of functions of one variable. Now I'm going to skip a lot of the underlying theory behind differentiation because I just am not entirely convinced it's a super important thing to be discussing here. But I want to get to how we take derivatives and what the derivative in fact means. Right, so let's consider a function f that maps a set x into y. The notation for this would be f maps a set x into a set y. You may also have seen this, y equals f of x. We can describe a function either way. Set f, or a function f maps a set x into y. Function f maps a set x into y. So what's happening is this function f is acting on the set x. X is the input, so we're putting a function on x, an operator on x, that is producing y. X is being mapped into y via a function or a transformation f. We'll be using this way more than we'll be using this. The derivative of a function f is denoted either f prime of x equals y prime, or dy over dx, the derivative of y with respect to x is equal to the derivative of the function f with respect to x. And the derivative of a function gives us the rate of change of that function. Another way to think of the derivative giving the rate of change is to say that the derivative gives us the slope of a function. You remember slope is equal to the change in y over the change in x. Well, the derivative is the slope. If you remember slope-intercept form, y equals mx plus b. M is the slope. B is the y-intercept. Which is where the line crosses y when x is equal to 0. X is the set of inputs. And y would be the set of outputs. Right, well, from slope-intercept form, we wanted the slope, well, it's m. It's the derivative of y equals mx plus b. So let's see. How does this work? Well, the function f of x gives the position of an object. Derivative is going to give the rate of change of the position. At some point, denote it, call it x0. Right, what is the rate of change at some point? If we want to think of this as a function of time, what is the rate of change of an object at some point in time, x0? Maybe a picture will help. Let's plot out a function y Now let's plot out y, which is a function of time. Now let's say we go golfing. All right, so if we go golfing, and you're going to tee up, hit the ball's going to presumably go in the air. Now if you are like me, where you haven't golfed in like almost 20 years, the ball's probably not going to go very far up in the air. But if it's a good golfer, right, they're going to tee off, they're going to hit the ball, it's going to travel some distance. It's going to go up, and then eventually it's going to go down. Actually, now that I'm saying this, let's not make this a function of t, let's make this a function of x. All right, so its position here, x0, is defined by this height, y0. So at this distance from where we teed off, the height is going to be y0. But now let's assume for a second that gravity just ceased to exist right here. What would happen to that ball? Well, if there was no gravity, there was no force pulling that ball back down to Earth. All right, we teed off, it's following a curve, and then boom, it would just continue to go in a straight line forever and ever and ever. All right, that straight line, you can draw it this way too, like that, is what's known as a tangent line. This tangent line is going to give me the instantaneous rate of change of this golf ball. It's going to give me the instantaneous rate of change. Because if there's no force pulling it back down, its speed is going to be constant, and it is going to keep traveling in a straight line forever and ever and ever. Right? The speed that it's traveling is the derivative. So how do we get to this tangent line? Fairly easily. Have another graph. Y is a function of x, and it will remain x this time. I'll plot out the function f like this. So this purple function is f of x. Now let's say I start at this point here, we'll denote it x. This is a point y, which is also f of x. All right. This is the function f evaluated at x. It's going to give me the height of the function when we are at this point x. Now what I want to do is I want to connect two different points. So I'm going to pick a point over here. I'm going to denote this x plus h, where the distance between x and x plus h is, you guessed it, h. All right, so this horizontal distance here is x plus h. This vertical distance Because here what we have, we've got x and x plus h. I have f of x plus h here, and I have f of x. So this vertical distance is f of x minus f of x plus h. Right, some arbitrary distance h evaluated. The difference between f of x and f of x plus h is going to be this vertical distance. Right? The evaluated points of the function x and x plus h. Now this right here is what is known as a secant line. If I were to connect these two dots, I get a secant line. The secant line crosses the function at 2 points. So let's take this distance h and divide it by 2. Well, h divided by 2. So this point here is going to be x plus h over 2. So at this point, if I were to evaluate the function f at x plus h over 2, I would get f of x plus h over 2. What we would do is we would draw a new secant line. Yeah. But with a smaller distance of h over 2. So the secant line with a smaller distance of h over 2. All right, well, let's do this again. We can actually do this an infinite number of times. If I make that h a little bit smaller, I'll get this. If I make that h a little smaller, I'll get this. And as you can see, what happens is eventually we converge on a tangent line rather than a secant line that touches only at one point. Touches only at one point, not two. The secant line touches at 2 points, but as we rotate the secant line in further and further and further by taking this distance h and making it smaller and smaller and smaller, eventually this tangent line will pivot around this point right here, f of x. It'll pivot to where it touches f of x at only the point f of x and nowhere else. This is what is known as a tangent line. How would we express this? Well, for those of you that have had calculus, you'll remember the limit definition of the derivative, the limit as h approaches 0 of f of x plus h minus f of x, I believe over h, I believe. I don't actually have the definition in front of me. But as we remember, that distance h gets smaller and smaller and smaller, and what becomes a secant line, because f of x plus h minus f of x over h is going to give us a secant line until that distance h approaches 0. As it begins to approach 0, that secant line becomes a tangent line. It converges to a tangent line, which is what I drew out here. So I'm not going to run through the limit definition of the derivative because honestly you don't need to know it. You won't have to evaluate anything with limits in this class. Let's instead talk about what the limit definition of the derivative will give you when you apply it. Consider the function y equals x squared. That's a pretty simple function to take a derivative of. Now if you remember how to take a derivative, or if you don't remember how to take a derivative, I'll make sure you know how to do it by the end of this lecture. How do I take the derivative of this guy? Well, I take this exponent and I make it the leading coefficient. I multiply it by the leading coefficient of this variable. So I'll have 2x, so I take this, drop it right here, right? And then I'm going to have the power of 2, but I always subtract 1. Every derivative I take, I will subtract 1 from this exponent. So I will have 2 times x to the power of 2 minus 1. How do I evaluate that further? Well, it just becomes 2x, or 2 times x to the first power. All right, if I want y equals x cubed, how do I take this derivative? Well, the derivative, dy over dx, is equal to 3, because I take this 3, this exponent, I multiply by the leading coefficient of x, which in this case is 1. So 3 times 1 is just 3, times x to the power of 3 minus 1, which is equal to 3x squared. So this will give me the rate of change of this function, this function. This gives me the rate of change of this function. All right, but there's something else that's kind of cool here, and that's, is there a way to evaluate what the rate of change is going to be at some point that is contained within the set x? So let's use this example here. 2x what is the rate of change of f of x at the point x equals 2? Well, we take x equals 2 and we plug it into the derivative of y equals x squared, which is y equals 2x. Well, I'd say y prime equals 2x. So y prime equals 2x, y prime, or, as I tend to prefer to use, dy dx. We'll see why I prefer dy dx. Oh, we plug that into the derivative. So what's the derivative? 2x. So I get 2 times 2 equals 4. All right, so the slope of y equals x squared at x equals 2 is 4. Let's draw that out. Remember, y equals x squared is a parabola. The slope is 4. All right, so for every 1 unit that I go forward, or 1 unit that I go to the right, I'm going to go up 4 units. What's the rate of change of y equals x squared at x equals 1? Well, do the exact same thing. I'll take x equals 1 and I'll plug it into its derivative. All right, so I'll get 2 times 1 is equal to 2. So here, at x equals 1, it's going to have a much shallower slope. This slope is 2. So if I go 1 unit forward, or 1 unit to the right, I will go up 2 units. So it's going to be a shallower slope than at x equals 2. So let's apply this in an economic context. Let's take the cost function of a firm. So we're going to have a function c of q, where c is the cost, q is the quantity. So the cost of producing a certain quantity will be defined by 3q squared minus 4 times q plus 10. All right, so this is going to give me the position. This is a position function. It's giving me the cost if we produce at some point q. So if I were to produce five units, q is equal to 5, c of q equals 5. Well, I plug in 5 for every q I see, so I'll get 3 times 5 squared minus 4 times 5 plus 10. C of q equals 5 is thus equal to 3 times 5 squared, which is 25, minus 4 times 5, which is 20, plus 10. C of q equals 5, therefore equals 75 minus 20 plus 10. C of q equals 5. 55 plus 10 is equal to 65. So the cost of producing 5 units is going to be $65. What about the marginal cost? Well, the marginal cost is going to be the additional cost incurred by the firm for making one more good. one more product, one more unit of output. How do I find the marginal cost? Well, marginal cost, which we write as MC, is the first derivative of the cost function. Well, marginal cost is the derivative of the cost function with respect to Q. So I would take C of Q, and I take its derivative. Right, what is the derivative of this guy? Well, I take the exponent, multiply it by the leading coefficient, subtract 1 from the exponent, take the exponent, multiply it by the leading coefficient, subtract the exponent, or subtract 1 from the exponent. And then here, well, let's take care of these two terms first, and then we'll get to this guy. Okay, so I'm going to have 2 times 3 q to the 2 minus 1 minus 4 times q to the 1 minus 1 plus, well, we'll leave that part out for just 1 second. Let's evaluate this. A question mark for that 10. The marginal cost is going to be 6q minus 4. This q to the power of 1 minus 1, q to the 0 just becomes 1. Right, this q, 2 minus 1, q to the power of now 1, where the exponent was multiplied by the leading coefficient. So I get 6q minus 4. Let's think about this 10. What is that 10? Well, this 10 is the c-intercept. It's the intercept of this cost function when we are producing 0 units. Right? It is a constant. It's not changing. It has no slope. Its slope is 0. So if its slope is 0 and I want to look at the slope of this function, well, this guy, this 10, differentiates to 0. It has no slope, right? It's just a flat line. There is no rise to its run. If there is no rise to its run, if we were to take its derivative, right, if we were to differentiate it, it would differentiate down to 0. So the marginal cost is 6q minus 4. Right? What's the marginal cost of making the 5th unit? So the marginal cost, q equals 5. Well, I would plug in 5 for q. Here I would say MC of 5 is equal to 6 times 5 minus 4. Marginal cost of 5 units is equal to 30 minus 4 is equal to 26. So the marginal cost, I make my 5th unit, is $26. Right, so if I were to go from my 4th to my 5th unit, 5th to 6th unit, right, because we're looking at 5, so $26 to make one more unit. All right, let's look at marginal cost, 6 units. What would that be? Well, I would plug in 6 for q, so I would get 6 times 6 plus 4. Marginal cost, 6 is 36 plus 4. Marginal cost, 6 is thus 40. So we can see if I'm making more units, the marginal cost, the cost incurred by producing one more unit of that good, one more unit of output, appears to be increasing here. So why is this useful? Well, in economics, remember we always think on the margin. We're always concerned with behavior at the margin. At the level is important, yes. However, when we are thinking about things in an economic framework, we are more than likely considering what is happening at the margin. So if the marginal cost is the first derivative of the cost function, right, we can sort of infer what's going on at the margin means what's going on with the derivative of our initial position function. What's going on at the margin of the cost function is the marginal cost. Right, what's going on at the margin of the revenue function is the marginal revenue. So when we think at the margin, what we're doing is we're thinking in the context, in the framework of a first derivative. Why is this important? Well, it's important because in economics, we are optimizing. Right? We are making the best of whatever situation we have. We are making optimal choices, optimal strategies, optimal policy functions. Meaning, what we are going to be concerned about is optimization. Right? When we are optimizing our particular function, we are trying to find the maximum or the minimum of that function. We are optimizing. So in a mathematical framework, when we optimize, we find the maximum or the minimum of a function. Well, if only we had a tool to help us find the maximum or the minimum of a function. Fortunately for us, we do. What is that tool? Well, that tool is in fact a derivative. We use the derivative to optimize. Why are we going to be using a derivative to optimize a function? Well, let's think about what happens at an optimal value of the function. Right, the maximum of a function the maximum or the minimum of a function, the derivative is 0. So let's look at this function y equals f of x, where x is some sort of parabolic downward opening function. Right? Well, here is the maximum. Call this x star. And y would therefore be equal to f of x star. All right, well, what's going on at x star? Well, if we were to think about what the derivative of this function was at x star, evaluated at x star, it would be a flat line. So I can say the derivative of f of x evaluated at x star is 0. No rise to the run. Right? No matter how far to the right or to the left I go, there is no vertical change. So for any horizontal change, at this point, there is no vertical change. All right, so the maximum of f of x is achieved when its derivative is equal to 0. Its derivative equals 0 at x star. So rather than evaluating a function at some point, what we're doing is if we evaluate a function, or the derivative of the function at some point x, what we're doing is we're going, okay, I know what this point is, but I want to know what its rate of change is at that point. In this case, when we're optimizing, we know what the rate of change is. The rate of change is going to be 0, but what we don't know is at what point that rate of change is 0. So, to optimize, you take the first derivative of a function and set it equal to 0. Let's do an example. Let's take y equals x squared plus 2x plus 5. All right, well, if I want to optimize this sucker, what I need to do is I first take its first derivative. So I'll say to optimize, first, I will differentiate y with respect to x. What's the derivative of this? Well, the derivative of it is going to be 2x plus 2. All right, because that 5 differentiates to 0. That 5 is a constant. All right, we can think of it as, in this case, this is going to be an upward opening parabola. This 5 is going to be shifting it up 5 units, right? But whether we are being shifted up or down any number of units, this parabola, the slope of the parabola is not changing. So if it's up here, the slope of the parabola at some point is going to be this. If we're down here, the slope is still going to be the same, right? So all this is doing is shifting it vertically, but it's not in any way, shape, or form changing the slope of this function evaluated at any particular point. So this guy goes to 0. So the derivative is equal to 2x plus 2. Right, well, okay, excellent. So we've got that much. What, though, is its optimal value? All right, in other words, what is the maximum or minimum of the function? Well, in order to find that, we set this equal to 0. And we solve for x. So, to solve for x, I'll subtract 2 from both sides. Right, because I want to isolate this x. 2x plus 2 equals 0, subtract 2. I get 2x equals negative 2. And I divide by 2. So 2x divided by 2 is equal to negative 2 divided by 2. All right, well, x is equal to negative 1. So when I optimize this function, I see that x is equal to negative 1. But what the first derivative does not tell me is whether this is a maximum or a minimum. It's a maximum or a minimum? Well, in this case, we would need to take the second derivative to tell us whether this is a maximum or a minimum. However, that's a little bit beyond the scope of this class. I'm not going to be making you check your second order conditions to see whether this is a maximum or a minimum. I can tell you what this is. What I can tell you is that there's a minimum that is achieved at x equals -1. All right, so the smallest value for y will be reached when x is equal to -1. So I'll have you play around with that a little bit. Plug in 0, plug in -1, plug in 1, plug in 2, plug in -2. Right, work on that on your own and see how that goes. This will conclude this lecture. Next we'll be talking about derivatives of functions of many variables. So thank you, and until next time, peace.